Why do people go bald?
Why are baboons' bums red?
What's a light year? Why do leaves go brown in the autumn? Why do monkeys like bananas? Why do some things glow in the dark? Why do animals not understand humans? Why do my receipts fade after a year?
Don't know the answer? Ask the Naked Scientists.
Hello and welcome to this week's Ask the Naked Scientist with me, Sue Marchant, and Dave Ansell. How's the word of science?
Oh, the science is quite good. So an interesting story the last couple of days about the star Betelgeuse. This is one of the stars in Orion. I think it's Orion's right shoulder.
Yep.
It's one of the biggest stars we know of. It's certainly the biggest apparent star. It's got a slight reddish tinge. It's quite difficult to see. It's quite dim. It's quite hard to see the colour of stars. But if you're somewhere really dark, it looks like reddish tinge. It's actually a red supergiant. It's a massive star. If it was in the solar system, it would spread out to the orbit of Jupiter. It's that big. It's absolutely enormous. And it seems to be changing size.
Oh.
Over the last 15 years, it's shrunk by about 15%. So it's sort of shrunk from just outside the Jupiter's orbit to just inside it. It's a supergiant star. It's a very, very massive star. It's about 20 times as massive as the Sun. It started off being a really bright star. It's only about 8 or 9 million years old. Our Sun's about 5 billion years old, so it's a really, really young star. But it's very, very big, and big stars burn very, very hot, and they burn very, very quickly. So a few million years ago, it burnt all of its hydrogen, and the Sun's still burning its hydrogen after 5 billion years. It's probably going to go for another 5 billion years on its hydrogen. But Betelgeuse ran out really quickly, used up all of its power, and then the core of it shrank and started burning helium and got really, really hot, and that sort of blew the outside of it out to be absolutely immense to form the supergiant. And what these supergiants do is occasionally they run out of, at some point it'll run out of helium, and the core will collapse even more, and then maybe it'll start burning something a bit heavier like lithium, and then keep smaller and smaller and smaller till eventually there's nothing left to burn and it collapses. The core collapses into what's called a neutron star. That's where basically the whole of the star gets turned into a giant nucleus of an atom, or just made out of neutrons basically, and that releases an immense amount of energy, and you get something called a supernova. And no, they don't really think that this change in size of Betelgeuse is probably not going to be going supernova, but it's quite close. And if it did go supernova, it would probably be all right for us, because we don't think we're one of the north, if we're not above the north or south pole of Betelgeuse. If we were, you can get really nasty gamma rays coming out. But anyway, it would be bright. It'd be brighter than the moon for a few months.
Wow.
It would be absolutely immense, a really, really bright star. It'd be like the full moon, even when there's no moon there at all. And it's possible this contraction is something to do with it going supernova, but to be honest, no one's ever seen a star go supernova, because it happens very rarely.
Yeah. And
no one's ever watched one all the way through and to see what happens. So
it was just a word that somebody saw on the back of a car somewhere and decided, that'll do for that star. No, I mean, it's just...
the people have seen the supernovas after they've gone bang, because they're really obvious.
Yeah.
Because you can see a supernova in other galaxies.
Right.
But no one's seen it kind of leading up to it, so we don't know what's going to happen. You never know, in a few years' time we might have a huge, new, incredibly bright star in the middle of Orion, and then it would collapse, and Orion would be missing his shoulder.
Wow, how bizarre. Well, Dr. Dave knows all sorts of things about all sorts of things. So, Dr. Dave, our first question for this evening, Pat in Lowestoft would like to know, do the scientists have any explanations for the phenomena that occurs in the Bermuda Triangle? They make plenty of films about it, but how do scientists view it?
It's an interesting question. There's certainly lots of theories for why things might get lost in the middle of the oceans at random. One of them is that sometimes waves get really, really, really big. There's sort of how big you'd expect waves to get, and all the models and how big people think that they could get, sort of maybe 60 feet high, or maybe 30 feet high. But actually, there've been quite good evidence for waves 60, 100, 120 feet high, absolutely immense waves. And if they hit a ship, which is only designed to take a 60-foot wave, then it's going to do serious damage. And I think quite a lot of ships just in the middle of a big ocean Sometimes you get really weird mixtures of seas coming from different directions. If suddenly, for some reason, you get lots of waves all kind of focusing into a point, then all the energy from the wave over quite a lot of area will get focused into one point. You get a really, really high bit of a wave. If that happens to meet a ship, you can cause complete havoc. Another really interesting one is something called methane clathrates. Methane hydrates. Basically, if you get water at very, very high pressure and mix in methane gas, you get methane from rotting vegetation. So at the bottom of the ocean, at the edges of the big oceans, you're getting lots of vegetable matter getting sort of swept out to sea and slowly sinks down. It then slowly rots and releases methane. And at high enough pressure and sort of low temperatures, you can kind of form an ice with methane in it. And then if you get a bit of an earthquake or something and you release some pressure over it, all that methane can get released very quickly. You get lots of methane bubbling up. It makes the sea look really... Then you get lots of bubbles in the sea. If you've got lots of bubbles in the sea, then it will reduce the density of water. If you reduce the density of water, then things will float deeper in it. And if that's enough to make the water come over the top of the boat, then your boat sinks. There's all sorts of odd theories like this, and the other thing is if you're flying through methane above it, it's either going to go bang when your internal combustion engine flies through it, or there's not enough oxygen so the plane stops behaving properly. So you can do all sorts of strange things. There's various other theories like this, but actually, if you look at the Bermuda Triangle and you look at the number of ships lost there, it's not that different to lots of other places in the world. Yeah, I think that people have done statistical analysis of it, and it's higher than average. Yeah, but there's lots of other places which are worse.
All right, well, maybe there's lots of unexplained phenomena out there in different places, but Bermuda Triangle just sounds great, doesn't it? Now, we've got Richard in Wickford. He says, aircraft black box recorder, why doesn't it float?
Yeah, the black box recorder on an aeroplane, it's designed to record everything which is going on, so sort of where all of the control surfaces on the plane are, where the elevators are, where the ailerons are, and what the pilots in the front are saying. So if something goes really badly wrong, you can work out what went wrong, put it back together. The idea, I think, if they floated, the problem is that you want to find it after a really bad crash.
Sure, yeah.
And the problem is if it floats up to the surface and then gets blown, it could end up
anyway, you wouldn't find
anywhere,
it.
and you're not going to find it. At least if it sinks, you know roughly where it is. It might be at the bottom of a really deep ocean, but you know within 10 miles radius.
They give a signal off, though, don't they?
I think they do give off some kind of signal for a while until the batteries get flat. So you got a better chance of finding it. So if you know roughly where it is and you can pick up that signal, then you can find it. Whereas if it's floating off into the distance, I think it's probably less likely to find it. And also, it's quite hard to attach it to a plane in such a way as it would float off and not fall off somewhere else when it shouldn't be.
All right, well, to Bob in Essex. Naked Science, he says, how do seeds know how to come up the right way? Is it to do with gravity? Would it be affected if they grew in zero gravity conditions? And is it possible to make an artificial gravity in space? Bob, that's loads there.
That is an interesting question. I'm going to start at the end. Is it possible to make artificial gravity in space? True gravity, the answer is no. To make true gravity, you just need something with mass. And unless you lug up a planet into space, there's not, or something with incredibly high density, an awful lot of mass there, you're not going to get attracted to it very much. So you're not going to be able to make any true gravity. You can make something which is actually virtually indistinguishable from gravity, and that's all you need to make something behave like a gravity is to accelerate it. So if you sat on a rocket which was accelerating you at 10 metres per second every second, that would make it feel like you were sitting on Earth. Pilots in planes, when they go around corners very tightly, they're accelerating very hard, and then they put what they call pulling G. If they pull 1G, then it's like they were sitting on the floor. If they pull 2G, it's like they're being pulled down with twice their normal weight. 10G, 10 times their normal weight. So you can put it on a rocket. You can do something similar and if you also accelerate when you go around a corner. It's basically a change in speed or direction. You need an acceleration to make you do that. So if you're going around a corner, then all the time, then you'll always have an acceleration. It will feel like you've got weight. So basically, if you go up into space and you make a round space station and spin it, then it will feel like you've got gravity.
Yeah.
As to how seeds know which way to go, I'm afraid I'm going to have to do some more research for you, Bob.
That's all right. We don't mind that, Dr. Dave. Now, we've got a caller on the line. We've got Dom. Hello, Dom.
Hello.
Hello there. You're through to Dr. Dave. What's your question?
Why does bleach make material white?
That's a very good question. Bleach is something which has got some extra oxygen in it. It's a very reactive. It's got very reactive molecules in it, and basically that will do what's called oxidizing things. Oxygen's actually a really unpleasant gas. The fact that it's really reactive, it will react with things. Essentially, it burns them. So what the bleach does is it will just go in, and anything which will burn, the things which are most sensitive to oxidization, sort of effectively burning, will get damaged first. It will damage all sorts of different things, and it's the reason why if you bleach your hair too often, it basically does it damage, and it doesn't behave very well, and it doesn't behave like it should do. But one of the first, a lot of chemicals, a lot of coloured chemicals are particularly sensitive to being oxidised, and so the bleach happens to attack those before it attacks the structure of things. So bleach happens to destroy coloured compounds before the others. It doesn't work on all coloured compounds. If you've got sort of iron oxide or rust, in fact, bleaching it often makes it worse. But most organic things which make colours, most pigments, are easily damaged by oxidisation, so easily damaged by bleach.
Have to be careful with our hair. Is that all right, Dom?
Yeah, thanks.
Thank you very much. Bye-bye.
Bye.
Bye-bye. Now, we're busy tonight with questions, Dr. Dave, so we'll press on. John in Tiptree says, is there any scientific basis for wormholes, not black holes, as proof that they exist? Is there proof that they exist?
Okay, a wormhole is essentially supposed to be something which connects two places in space and time together.
Right.
So sort of a tube in space and time. And I think there are some the kind of theories which we use to look at this kind of thing is called general relativity. It's something which Einstein worked out, in fact, about 1918, 1919. And it's great, very complicated. And there do appear to be some solutions which do let you make these tunnels through space and time, and so you can kind of go from one place to another, possibly much quicker. However, the only ways people seem to be able to make the maths work is involving materials we don't have, things which act negative, with sort of negative gravity. Otherwise, the wormholes close up immediately and you can't hold them open. And as far as we know, none of these exist. We haven't found anything that existed. We've never seen anything which could be a wormhole, so there's no evidence for them, no.
All right, well, we've got a live caller now, and this is Mark. Hello, Mark. Hi, Mark. Can you hear us all right?
Yes, just about.
Right. OK, what's your question to Dr. Dave?
Well, it's two questions into one, really. It's about teleportation. I heard that they've teleported in Harvard University a quark last year, and this year they've actually done teleported an atom. Is this true, or am I mishearing things?
It's not a story I've heard. They've certainly teleported photons. Basically, what they mean by teleportation is by taking all of the quantum properties, all the properties of one object, and then giving them to another one somewhere else.
Right.
So you're not actually transporting the object, but you're taking the properties. So if it was moving west at 10 miles an hour and it happened to have this much charge and spinning in this direction, you would then take another atom somewhere else and you'd be able to make it move at exactly 10 miles an hour and spinning in the same direction. The problem is normally because there's a thing called Heisenberg's uncertainty principle, which means that you can never know the speed and direction of the speed and its position and the position of anything perfectly accurately. If you know the speed of it perfectly accurately, you've got no idea where it is, and if you know exactly where it is, you've got no idea how fast it's moving.
Okay.
So this is really, really difficult. Some people do seem to have come up with ways of doing this using some clever quantum tricks, using something called entanglement. And they've certainly done photons. And actually, I've looked this up, and they do seem to have managed to teleport the properties of one atom to another one.
Oh.
So yes, I think it is possible. They do seem to be saying so. Yes.
So we're closing into Star Trek sort of reality now, then?
I think it's going to be a while.
Do you think it will be possible in the next 20 years?
I think I would be very, very surprised in the next 20 years. I think you'd be better off waiting for someone to... I think it's more likely the only chance you've got to live to see it, I think, is if they manage to solve a solution of eternal youth. And then possibly in a couple of thousand years they might get there.
I've got that.
Okay, thank you.
Mark, thank you very much indeed.
Bye.
Bye. If you're enjoying Ask the Naked Scientist, then you might like to check out The Naked Scientist, our regular roundup of the world's best science. Each week we take a look at the latest science news, talk to top researchers working at the coalface of discovery, and also get our hands dirty with a science experiment that you can join in with too. So make it a date and prepare to strip down science on the web at nakedscientist.com/podcast. Right, let's go back to our questions here. Mike says, Dr. Dave, why do TV adverts sound louder than a normal film or regular programme? Yes, I know, it's mad, isn't it? There you are, there's quite a bit in a film and you fight to find what you've done with your remote control, or even, get up off your seat and move the telly. And then suddenly there's a break and they're so loud. What is the reason for that?
This is a clever piece of audio tech. It's basically what they do to the sound. The loudest bits of adverts are the same volume as the loudest bits of a film or a normal programme. It's just that a normal programme doesn't stay that loud very much. What they've done with an advert is it's a system called compression. What they do is they have a little piece of electronics which can amplify the volume or increase and decrease the volume of it. And if the piece of electronics notices that the advert's in a quiet bit, they turn up the volume. And if it gets to a loud bit, so the volume, so it's always loud. So whenever, even if someone would actually be talking quite quietly, it automatically turns the volume up. So the volume is it's at the same maximum volume as a normal program, but it's always there. So it feels a lot louder because everything is as loud as your radio can put out. And so without having the loudest bits louder, it can feel a lot louder.
Now, we've got Tony on the line and Mark the trucker on the A14. Thank you for your question. We'll be coming to that very shortly. But first of all, here's Tony. Hello, Tony.
Good evening, my dear. It's about the things like the Earth, the Moon, everything spins, right?
Yeah.
Now, does everything spin in space? I mean, the big galaxies, everything, and why? And how does it manage to keep its axis at the same angle?
Pretty much everything is spinning. Essentially, everything, the whole universe started off fairly spread out. There's some sort of random variation, so some bits were spinning slightly one way and other bits were spinning slightly the other way.
Oh.
And if you ever watched an ice, and then it sort of collapsed inwards to form stars and planets and things, and if you ever watched an ice skater on TV...
Yes.
When they do the spins, they sort of start off spinning slowly with their bum stuck out one way and their legs stuck out the other way. And then they kind of pull themselves up so that all their weight moves towards their axis of where they're spinning about. And they spin faster and faster and faster, and they end up standing up dead straight, spinning incredibly fast.
Fast, yeah.
Because as you move mass inwards towards, as if it's spinning around a point, and if it slowly moves in towards that point, it spins faster and faster and faster because it's got less far to go round. And it's also gaining energy as it falls inwards, so it spins faster and faster and faster. And so only minute amounts of spin, the big bits of the universe wouldn't spin in billions of years. But as they collapse down and down and down to something the size of a planet, it's spinning quite fast.
And the black hole would be very fast, I imagine. The actual core of it.
Certainly, very dense things do spin incredibly fast. You get things called pulsars, which are thought to be neutron stars, which is sort of the one thing less dense than a black hole, and they can spin around hundreds of times a second.
Good Lord.
Yes, they actually lose energy and slow down, but they do spin incredibly fast. And basically, things naturally will point in the same direction all the time if there's no force on them. in the same way that things will carry on go. If you push something, it will carry on going in a straight line. Newton's laws, it will carry on going in a straight line unless you apply a force. Things will carry on spinning on the same axis unless you apply a force.
Like a gyroscope?
Like a gyroscope, yes.
Right.
It's sort of just the natural behaviour of it. Although if you do apply a twisting force, which is called a torque, then the direction can change, a bit like when a gyroscope feels gravity and it processes it. The direction it's pointing in sort of slowly orbits round and round.
Because the Earth always points in the same direction, doesn't it?
It does.
I mean, as it goes round the sun, it points in one direction. That's why we get seasons, I believe.
It is, you're right. It does certainly, over the kind of period of a year, it will point in the same direction. But there are little twisting forces applied to it by the Moon and Jupiter and the Sun. And they actually cause the direction to precess over thousands of years. And so it doesn't. It will change because there are forces acting on it. It does change slowly over thousands of years. I think 10,000 years it will go all the way around. It might be even quicker than that.
All right, Tony.
Well, yeah, we might get cold weather or something because of that. That's why the climate changes.
There are some
over millions.
I think the direction less so, because that just affects where we are around the orbit when it's northern hemisphere summer. But the amount of tilt on the axis does change as well. I think that's actually the 10,000 year cycle, and that will change, and that will change the climate a bit. And that is possible. Some of these cycles, there's lots of different cycles like this, and some of them might correlate with ice ages.
Right. Thank you very much.
Thank you, Tony.
And thank you, Sue.
All right. Bye-bye.
Bye.
Now, Mark the trucker on the A14, his question is, the universe is getting bigger, so they tell us. Generally, when things get bigger, they stretch and get thinner. So could that be an explanation or contributor for global warming?
The universe is certainly expanding. It's thought that the bits which are expanding it's not everything that's expanding. It's the bits, it's big empty spaces. So the bits between the galaxies are expanding quite far. It's certainly expanding, but galaxies don't seem to be expanding. So, and the Earth certainly isn't expanding. So it's sort of empty space which is expanding, and everything's getting further apart. So it's unlikely that would be having anything to do with the Earth for a start. It's also expanding over billions of years, whereas global warming seems to be happening over tens of years, which makes it unlikely. And also, in general, when you let things expand, they tend to get colder. If you, for example, take a aerosol can and that's got a load of compressed gas inside, you spray it for a long time, you ever notice it getting cold?
Oh, yeah. Yeah.
That's because the gas is expanding. When you let a gas expand, it cools down. So, and the universe, as it's expanded, has cooled down. Just after the Big Bang, as far back as we can see, the temperature was hundreds of thousands of degrees centigrade. It's cooled down and cooled down. It's actually far back as we can see, it's probably thousands of degrees centigrade. But as the universe has expanded, it's cooled. So I would be very surprised if it had anything to do with global warming.
Dr. Dave. Now, we've got an email here from Nick who says, Dr. Dave, why does light travel faster than sound?
That's a very interesting question. Fundamentally, it's because the force which affects atoms, so the force which pushes atoms around, the electromagnetic force, is actually transferred by particles, essentially photons, so essentially particles of light, and they travel at the speed of light. And so sound is basically, if I hit one end of this table, then that vibration travels along the table and gets the other end. Yeah. If I wobble the air here with my throat, the air wobbles and then that wobble travels towards the microphone. Yeah. And so, the forces between the atoms the force travels between the atoms at the speed of light. And then in order to move the atom, you've got to apply that force for a while because the atom's got some inertia. So it takes a while to move that, accelerate it and move it so as it can then bash into the next atom, which can bash into the next atom, which can bash into the next atom. I mean, there's absolutely no way it could go faster than the speed of light, partly because the fastest anything can go is the speed of light, and more fundamentally because the force between all the atoms is transferred by essentially light. And so, essentially, yeah, the fastest, the highest speeds of sounds are associated with very stiff materials because the forces between them are very large. And one of the highest speeds of sound is probably in diamond, which is incredibly stiff material, which is about 12 kilometres every second.
Wow.
Whereas in air, it's about a third of a kilometre a second, the speed of light, the speed of sound. And getting much faster than that, you need to go to something incredibly exotic, like in the centres of the stars. But definitely never anywhere near the speed of light, which is 300,000 kilometres a second.
Wow. Nick, I hope that answers your question. Now, Anne has said, I can remember a road atlas I once had, which was marked with north in 3 directions. There was a true north, magnetic north, and the other one I cannot remember. Can Dr. Dave help?
Yes, she is right. Most maps have got various different norths. One of them is true north. That's a direction to the North Pole, which is where the Earth is spinning about. Mm-hmm. The other one is a magnetic North Pole. The Earth is essentially like a big bar magnet, and there's 2 ends of the bar magnet, and they roughly line up with the north and south true poles, but they're not quite. They're a bit offset. I mean, I think by sort of 10 or 15 degrees, I think the differences can get very large. I think especially around up north, somewhere in northern Canada. So magnetic north is quite different, and it also changes over time. The North Pole wanders about. The magnetic North Pole wanders about on the Earth. So that's 2 of them, and the other one is grid north.
Grid north, that's the one.
And that's the direction in which the lines on your map are pointing, which isn't necessarily the same as true north. The problem is that if you're trying to put a grid on Earth, it's very easy to draw a grid on a flat piece of paper. Yeah. The problem is you're trying to put it on a curved thing. The Earth is curved. Yep. If you try and draw a proper grid on an orange.
Yes. Oh yes, I'm with you now. Because when you said, I thought you said loins first of all. I thought, no, it's getting like me. But no, you're right here because I've just tried to do that one there. Well, I mean, yes, it's curved.
That's partly it's curved if you do it on a curved piece of paper. But if you do it on an orange, the problem is you want your grid so all 4 sides of the grid are 1 kilometre long. Yeah. And they sort of join at each other at 90 degrees. But the problem is, the Earth is curved, and if you imagine a really, really big square, grid square, which starts off at the equator and goes north up to the North Pole, and then turns 90 degrees, and then comes back down to the equator, then you've got something with 3 corners, all of 90 degrees, but it all joins up because the Earth is curved. You couldn't do that on a flat piece of paper. And so if you try and draw a grid on a curved surface, it doesn't work very well. And so you're trying to pretend that the curved surface is flat, and so you have to bodge it a bit, and the bodge comes out, meaning that the grid lines don't actually point north anymore.
John, the vintage radio engineer, why, Dr. Dave, in your opinion, are staples still used to attach paper magazines together as they can rust? Wouldn't it be better to use plastics or something else? Yes, absolutely, because of environment and stuff.
Well, I mean, I guess it depends how long you want to keep your magazines, I would have thought. Yes, staples can rust. I mean, there's lots of ways around it. You could make the staples out of a metal which didn't rust. I mean, you can make them out of stainless steel. That's more expensive. I think fundamentally it's price. There's lots of ways around it, but they're probably all more expensive than staples, which are very, very cheap. And also, if you want to recycle the paper, you can kind of mash it up and then apply a magnet and pull all the staples out. So yes, there are lots of other ways, but they're all expensive, and the rusting staple is only an issue if you want to keep your magazines for many, many years, somewhere slightly damp, and most magazines aren't kept that long.
Nigel in Mulgrave, he asks, what is the universe expanding into?
That's another interesting question. As far as we know, the universe isn't expanding into anything. The universe is 3-dimensional. We live in a 3-dimensional universe. And it appears that everything is getting further apart from each other at an even rate. And it's a bit like if you imagine a balloon and the surface of the balloon is the universe. So that on the surface of the balloon, it's only 2 dimensions. You can only go in the X and Y kind of directions. And if you imagine putting some blobs on that for galaxies, and then if you blew up the balloon would get bigger and everything would get further apart. Yeah. But but in the two-dimensional universe, on the surface of the balloon, if you're an ant, you wouldn't really. The balloon isn't expanding into anything. Everything's just getting bigger. So the universe, as far as we know, the universe is just expanding, and it's thought that it's not expanding from anywhere to anywhere else. It's sort of expanding into a fourth dimension or various other dimensions. And so it's not just the whole of space is getting bigger. The whole universe originally started off at a point, and the space was very, very small, and the space has just got bigger and bigger and bigger.
But we don't know why. That's it for this week. Our doctors will be back with me next week for more Ask the Naked Scientist. But don't forget, you can also catch them on the Naked Scientist podcast, which you can find on the Naked Scientist website, www.nakedscientist.com.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.